Sorry guys, I ran out of time on that video, so sorry for the choppiness. We had left off, we were going to calculate this probability right here. What is the probability of not getting 3 heads in a row? Okay, 2 ways to go about it. One is, again, anytime you want probability, find the number of ways to pull this off, to achieve it, divided by the total number of options out there. Well, there's 8 options out there, we said, 8 outcomes. And how many of those outcomes are not heads, heads, heads? Well, that's 1, 2, 3, 4, 5, 6, 7. 7 out of 8 of those outcomes are not heads, heads, heads. Okay, another way to do this, though, is to utilize complement. If you notice, this guy and this guy are complementary events, right? So one thing I could have done is I could have said, or the probability of not heads, heads, heads is the same as 1 minus the probability of heads, heads, heads. Right? If it's not raining, it's 1 minus the probability that it's raining. So this is 1 minus 1/8, which would also be 7/8. So another way to go about it. Now, on the last video, I said what can be tricky is the wording here. So here we calculated the probability of not getting all 3 heads. Here they're saying, what is the probability of flipping a coin 3 times and getting at least 1 tails? Think about that for a second. At least 1 tails. That means 3 tails are good, 2 tails are good, 1 tails is good. In other words, it's the same darn question. It's everything except the heads, heads, heads case. So they've phrased it very differently, right? But the probability of getting at least 1 tails is the same as the probability of not getting heads, heads, heads. Not all heads. You got to have at least 1 tails in there. So it's tricky because it's the same answer. It's 7/8, right? There's 1, 2, 3, 4, 5, 6, 7 ways to get at least 1 tails out of 8 options. But again, what they're doing is they're basically asking you the same question using totally different verbal descriptions of it. So we got to be careful with that. Okay. Now, if I could just kind of draw an arrow, sorry my notes are getting all crazy, but if I draw an arrow back to that question, the probability of getting heads, 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 when you flip a coin 3 times, we said the likelihood is 12.5% chance you're going to do that. Would you consider that unusually low probability or an unlikely thing to happen? It's low probability, that's for sure, okay? But in mathematics, we have sort of a cutoff for what we consider mathematically unlikely or too low of a probability to be considered a normal occurring event. And our default for that is going to be 5%. Okay, so we're talking about when do we consider something highly unusual or very unlikely. We'd say that an event is unlikely if the probability is small, very small, such as 5% or less. Okay. So if you're finding the probability of an event and the probability comes out under 5%, then we would consider that to be very unlikely and sort of an anomaly. Okay. So here they ask, is it unusual? It says we can find the probability of more than one event by multiplying the probabilities, and we're going to talk more about that later. Eventually we'll get into the multiplication rule where we'll talk about this. Sorry, I had to pause the video real quick. Someone came into the office and trying to jump back into this now. So it says we can find the probability of more than one event occurring by multiplying the probabilities, and we will cover that more in depth later. We'll see why this is needed in just a second. So it says, what's the probability of flipping a coin twice and it landing on heads both times? And would we consider that unusual? Well, again, the easiest way to calculate probability would be look at its sample space. Okay, so let's think about the sample space for this scenario. All right, so I'm going to flip a coin twice. And I want to list every outcome that can happen when I do that, when I flip a coin twice. Well, I could get heads and heads. I can get heads and a tails. I can get a tails and a heads. or I could get tails and a tails. And again, what I did is I went through all the ways to get 2 heads, 1 heads, 0 heads. I kind of exhaust the possibilities before I move on. Having the sample space makes life easy. Right? That's what I'm looking for. I want the probability of getting heads and heads. Well, I can see that there's 4 outcomes available. Only one of those is, or only one way to achieve that success. So one way to pull it off out of 4 possible outcomes, 1/4 is the probability. Not bad when you have the sample space. But here's why they told us about this little multiplying thing. As soon as they up the rules, this becomes ridiculous. What's the probability of flipping a coin 10 times and having it land on head or heads 10 times? And would we consider that unusual? I guess I should finish this off. They asked, is this unusual? This is 25%, not below 5%. So not considered unusual. But here I'm going to flip a coin 10 times. Now, if we tried to do this sample space, we would quickly be outnumbered. One thing you'll notice, or one thing we could do is when you've got 2 outcomes, okay, heads or tails, and I'm flipping the thing twice, I could raise it to the 2nd power and I could see that there would be 4 things in my sample space. Let me scroll back up here. When I was flipping a coin 3 times, so again, 2 outcomes, 3 flips, 2 to the 3rd is 8. There should have been 8 outcomes, and there was. But now here I'm flipping a coin 10 times, so I've got 2 options, heads or tails, 10 flips. 2 to the 2nd is 1024. That's how many things would be in my sample space. It'd be impossible to write it out. I mean, the first option would be heads, 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 heads. Oh my gosh, 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this is where it gets out of control. Is I could have 9 heads and 1 tails. Well, think of all the various combinations. I could have 9 heads and 1 tails, and then 8 heads and 1 tails, and then 7 heads and 1 tails. You would end up getting 1024 different things in here. So in other words, the sample space in this case, it's not a doable option. And that's where we are going to need to learn about additional probability rules, is because those sample space is great and it really helps us calculate probability easily. As soon as the rules of the game change, as soon as the sample space becomes too hard to calculate or too impractical to calculate, then we can't just count up the number of wins over the total number of outcomes. So anyways, they gave us this clue here and said if you want the probability of 10 heads, what we can do is we could take the probability of getting 1 heads times the probability of getting another heads times the probability of getting another heads. We could do that 10 times. And I know each of these probabilities, probability of getting a heads when I flip a coin is 1/2. And when I flip another coin, the probability of getting heads is 1/2 and 1/2, all the way down. And since I did it 10 times, what I've really got is I've got 1/2 to the 10th power, which is 1 over 1024. Probably really low. Oh yeah, that would be 0.0976%. That's well below 5%. Thus, highly unusual or unlikely. Highly unlikely to happen there. Okay. I've got 5 minutes left on this video, so I'm going to try and whiz through this next page sort of quickly. Again, what I'm hoping is that for all of these, I hope you're pausing it, a lot, and then thinking about the problem, trying it on your own, and then hitting play to see how you did. So let's do these 5 examples if we can in the 5 minutes we got. It says, when Mendel conducted his famous genetics experiment with peas, one sample of offspring consisted of 428 green peas, 152 yellow peas. Based on those results, estimate the probability of getting an offspring pea that is green, and is that result reasonably close to what Mendel expected at 3/4? Let's see. We want the probability of getting a green pea. Okay. Probability is find out how many ways there are to pull off a success there, divided by how many outcomes there are. Okay. Again, pause it and try all these problems, please. But let's see. Of these peas I've got 428 green peas available. And out of the total number of peas I've got 428 plus 152. Okay. And so I've got 428 out of 580. That would be a 73.8%. which is pretty darn close to 75% what Mendel expected. Okay. Let me go to number 2. Again, sorry to go fast. I'm just trying to beat the clock here. On the first date, Kelly asked Mike to guess the date of her birth, not including the year. What is the probability that Mike will guess correctly? Okay, well, if you think about it, I want to find the probability of guessing someone's birthday, just the date. How many options are there? How many outcomes are there? In other words, how big is the bucket of guesses I can pull from? There's 365 days in a year, so that would be the number of outcomes that I could possibly select, that many different days, and only one of those days are Kelly's birthday. So 1 out of 365 would be the probability of guessing someone's birthday just on the date, which, if you put it in a percent, is 0.27%. They ask, would that be unlikely? Heck yeah. Very unlikely. Because it's well below 5%. So if you were Kelly and Mike did guess your birthday correct on the first try, would you believe that he just made a lucky guess, or would you think that he already knew what was going on there? It would be really, really hard to make that guess. Very unlikely. So if he did guess it right, it's probably that he was doing some Facebook stalking or something and knew your birthday ahead of time. Okay, let's try this one. It says, in a survey, 169 respondents say that they never use a credit card. 1,227 say that they use it sometimes, and 2,834 say they use it frequently. What is the probability that a randomly selected person uses a credit card frequently? So I want the probability of using credit frequently. All right, again, probability is looking for the number of outcomes or the number of ways to pull off a success, right? How many of these people, how many of them raised their hand when I said, do you use your credit card frequently? And that would have been this number. 2,834 said, yes, I use my credit card frequently. And the grand total of people that responded to the survey, well, there was 169 here, and over 1,200 here, and 2,800 here. So this is the size of the pool that we could have selected from, right? Those were the total number of outcomes that could have occurred. 2,834 over that's 4,229. Which comes out to 67%. 67% of respondents said they use credit cards frequently. This says, how are these results affected by the fact that the responses were obtained by those shopping or posted a survey on the internet? Well, I've got 20 seconds here. I'm going to just stop it. Be back in a minute.